Magnetism is the final part of circuits, and it's sort of a standalone unit, but you'll see at the end of this that magnetism is related to electric current. So the first thing that we can talk about to sort of set the stage for this is that in 600 BC, or sometime around there, there was the discovery of a type of rock, and this rock is called lodestone. And what it did was, lodestone attracted iron. So these people, this was in China, found that pieces of iron would get attracted to this. And then they figured out if you took a little sliver of this iron and you rubbed it against the lodestone, the little sliver would become magnetic itself. So if you took this little sliver and set it on a leaf, and you put the leaf in some water, the leaf would orient itself so that it always pointed north. And this was the discovery of the first magnetic compass. So what is the definition of a magnet? Well, a magnet is just any material that produces a magnetic field. So that, of course, begs the question, what's a magnetic field? And we'll do that in just a second. But I want to talk about two types of magnets. There are permanent magnets, and there are temporary magnets. So the difference between these two is a permanent magnet is a material that it constantly or persistently has its own magnetic field. So it doesn't really matter what you do with it. You can move it around or whatever, and it keeps its magnetic field. A temporary magnet would be something like a piece of iron that only becomes magnetic when you move it into a permanent magnetic field. Or we'll see in the case of an electromagnet, if you take a piece of iron and you wrap it in wire and pass current through the wire, it will become a magnet while the current is flowing through it. So two types of magnets. So what is a magnetic field? Well, first off, in the Regents curriculum, you don't need to know this, but the symbol for magnetic field is an uppercase B. And I do think if you're going to go on and do some more physics in college, that's worth knowing. So what is it? A magnetic field is the magnitude, and remember that magnitude means strength, and it is the quantity of something. The magnitude of the force that orients a compass needle. And because it's orienting it, that means it includes direction. So if it includes direction and it has strength, therefore it is a vector. So magnetic fields are vectors, very similar to electric fields, but instead of having a force on a charged particle, magnetic fields have forces on magnets. In this case, we're talking about compasses. The unit, also in the Regents curriculum, you don't need to know this, but I think it's worth knowing that the unit is called the Tesla. So let's look at a situation here where we have a magnetic field, and the magnetic field is moving along like this. So it's pointing up and to the right. So according to the definition, that means that our magnetic field will point in the same direction as the compass. So I'm going to color this in and always use the dark side to be the north and the light side to be the south. So the compass needle points in that direction. That's the direction of the magnetic field. So what can we say? We can say that magnetic fields go from north to south. But there is an exception, and that exception is inside a magnet. So if we go into the material itself, inside the magnet, they go from south to north. And there's a little way to remember this that I use, a little trick, and it's the word lines. And remember, in lines, they go from north to south with the E, except inside a magnet, they go south to north. So why are magnets magnetic? Why do they make magnetic fields? Well, it has to do with unpaired electrons. So in certain materials, the unpaired electrons can get aligned better than other materials. So this is because they have something called spin. And when the electron spin aligns, it produces something new called a domain, a magnetic domain. So the way that we represent this is just with an arrow. So the electron spins in a certain direction, and that's an oversimplification of what's happening. It's not simply a spin like a spinning top, but you can think of it as that for now. It spins in a certain direction and produces a little domain that points in a certain direction. And because in most materials, the electrons are spinning in lots of different orientation, the domains are all jumbled up. So if we take a metal, just an ordinary metal that's not a magnet, so this is a non-magnet, then the domains inside that would be all jumbled up. They would be pointing in all sorts of different directions. So that's how we know that that is a non-magnet. However, in a magnet, now we're talking about a permanent magnet now, a magnet that holds its magnetic field, the domains are all aligned. Why? Because all of the electron spins are aligned in the same direction. So we end up with something that looks like this. Now think about the direction that they're pointing. Well, we said that magnetic fields point north, so that would be our north pole, and this would be our south pole. But what about temporary magnets? Let's say we have a magnet like this that's a permanent magnet, and off in the distance over here we have a magnet that has unaligned domains, so it is not a magnet. If we bring this closer, when it gets closer, the magnetic field from this will align the domains from the temporary magnet. Now, like I said, there are certain materials that do this better than others, and for the most part, you should know that this is all of the iron, steel, nickel, and cadmium are the other materials, but really we're going to focus on iron. We're going to focus on steel for this. So if we have a permanent magnet, and this is the north and south pole, and we take a little compass, our compass here is going to be, the dark side is going to be our north. So the north is pointing in the direction of the magnetic field. And if we take this magnet and move it, or sorry, the compass, and move it into different locations, it will map out the direction of the magnetic field. So what does that look like? Well, we can just put our vector arrows in here to show the direction of the magnetic field. So if we look at a bar magnet, the shape of the magnetic field looks like this. Now, the concentration of the lines is called magnetic flux. And all this means is the strength. That's the strength of the field. And it is the concentration of the lines in a given area. So if we look here, right in here, we have lots of lines concentrated. So this is the strongest part of the magnetic field, and also over here. Also remember that magnetic fields go from north to south, like this, but inside the magnet, they go from south to north. Just like with electric fields, magnetic fields, and this is true of all different types of fields, the lines never cross. So a lot of times they'll give you a multiple choice question and they'll say which one represents the magnetic field, and some of the choices will be crossing lines, so you know that those are incorrect. So we know that magnetic fields go from north to south. Here we have the ends of two bar magnets that are close to each other. What's the magnetic field going to look like between them? Well, if we put a compass in here, the magnetic field lines would go straight across from north to south with a little bit of curvature up here. And you can see a lot of similarities with this between electric fields. But remember, magnetic and electric fields are different. So from a north pole would repel, but it's the vector sum of these two. So as it repels from the north, it pushes away in this direction. It is also going to be repelled by this north pole. So it's going to do something like this. And this one will do the same thing, and they'll get close to each other, but they will never touch. So they're going to curve away like this, like that. And the same thing's going to happen down towards the bottom. We're going to have magnetic fields moving like this, and again, away from the north towards the south. So a south-south magnet is going to be the same thing, except the arrowheads are going to be going in the opposite direction. So they're going to be attracting, and they're going to have that same sort of curvature here that we see with the north-north, just opposite directions. And then finally, there's something that you should know about, which is a horseshoe magnet. And in a horseshoe magnet, the ends form the poles. So this is going to go from north to south, like this. And there is a weak field in here. It's very weak down here. So the flux is greatest up here. So that means the field has the greatest strength at this point. So we need to talk about an added tricky part of magnetic fields. So let's just start out with a piece of mass. So this would be an uncharged piece of mass, just a lump of clay or something like that. Because it has mass, it has a gravitational field. But an electron or a proton, we could do this for a proton too, also has mass. So it also has a gravitational field. But because it has charge, it has an electric field. So an electron sitting by itself, or a proton sitting by itself, has two types of fields, gravity and electric. But here's where it gets tricky. So we have an electron, so we know that it has a gravitational field, and we know that it has an electric field, but if it is moving, it also has a magnetic field. So the main thing that you need to know here is that moving charges, and this could be true for a proton as well, moving charges have magnetic fields. That's a tricky idea. And it's even trickier because we could have an electron that we start to move, or we could have a stationary electron and we move past it. In either of those situations, as long as there's relative motion, a magnetic field gets produced. So what happens? Well, let's say we have a magnet that has a north pole here and it's producing a magnetic field. If an electron moves through this magnetic field, the electric charge has no effect. But because it's moving, it has a magnetic field spinning around it. And when it moves through here, these two magnetic fields will interact and it will produce a force and it will push on the electron, and the electron will actually go in a curved path. Now, we'll learn about this in a little bit. If the electron is moving parallel to the field, then there won't be that force, even though that still has a magnetic field. So we know that electrons have charge, and we know that moving electrons have a magnetic field. So what this is a cross-section of wire. And this wire, it's just cut off, but this wire continues around to a voltage power supply. And that power supply is making current flow through the wire so that the wire current is down. Now, we poke that through a piece of cardboard and put some compasses on it. Well, the compasses are going to show us the magnetic field because we know that electrons flowing produces a magnetic field. In other words, we can say current flow produces a magnetic field. So if we take our fingers, the rule is to take your left hand and to point your thumb in the direction of the electron flow, the direction of the current, and curl your fingers. And the curling of your fingers will be the direction of the magnetic field. All of these little dark parts are our north poles, so they're pointing in the direction of this curl. If we reverse the current flow and made the current flow up, then the magnetic field would switch and the compasses would point in the opposite direction. But because it's very difficult to ask multiple choice questions in 3 dimensions, there is another method that's used so that you can do this on a 2-dimensional piece of paper. And it's to use dots to represent something coming out of the page and an X moving into the page. So what that dot is would be a magnetic field that's coming straight out of the page, and the X would be a magnetic field that's going into the page. And how can you think about this? Well, imagine an arrow, and the arrow has feathers, and there's 4 of those feathers. The back side of the arrow looks like an X. The front side of the arrow, the point, looks like a dot. So if someone is over here and here's a piece of paper, they would see the arrow coming through the paper and they would see a dot coming out of the paper. Whereas someone from behind would see the tail of the arrow, they would see that X, so they know that the arrow is going into the page. Pierce the plane and is traveling out of the page at right angles to it. An X or cross is used to represent a vector that is receding from the observer and is piercing the plane by traveling into the page. The method for determining the direction of this vector is to use a technique called the right-hand rule. So how can we use this to figure out questions with the direction of current flow? Well, let's say we have a segment of wire like this, and we have the current flowing up like that. What's flowing up? Electrons. What do moving electrons have? A magnetic field. So we point our thumb up and we curl our fingers around. So our fingers on this side are coming out of the page. So we would represent that with dots, and this side it's going into the page. If we reverse the flow and we said that current was flowing down, in this case we point our thumb down, curl our fingers, and on this side it's going into the page, and the magnetic field is looping around and over here coming out of the page. So what's represented here? A whole bunch of dots. Dots represent a field that's coming out of the page towards us. So if we have a wire that crosses this field and it's perpendicular, so the wire crosses perpendicular to the magnetic field, then we will get a force on the electron. So this is the opposite situation. So as it crosses this field, we will get a current flow in the wire. Now, I'm not going to redraw it, but you can picture if these were X's, then it would still be perpendicular, and it's crossing perpendicular to that magnetic field, so we would still get current flow. The main idea is that when we have perpendicular crossing of a wire with a magnetic field, then current electrons will start to flow in the wire. And that's true whether the magnetic field is going into the page or whether the magnetic field is coming out of the page. Here's a side view of the same phenomenon. Our arrow lines, our vectors here, represent a magnetic field B. And if we have a wire in which the current is flowing parallel to the magnetic field, so I is parallel to B, then we get no force whatsoever. So there is no force on the electrons, therefore no force on the wire. But if we have the current flowing perpendicular to the magnetic field, so now I is perpendicular to B, we get the maximum force possible. Now, why do I say maximum force? Because in this orientation we get nothing, and in this orientation we get the maximum. Well, wouldn't it be true if we oriented it this way, that some part of this is acting perpendicular? So that component would be a partial force, and it wouldn't be as strong. The steeper it is, the closer it is to perpendicular, the stronger the force. The closer it is to parallel, the weaker the force. So when we have a situation like this, where we have our current flowing partially perpendicular, then we get a partial force. If we have a coil of wire, and we take a magnet, and we move this magnet through the coil of wire, then we have a changing magnetic field in this coil, in these loops. So what that does is it produces current flow. Now, if we take a magnet and we just place it in here and don't move it, we don't have a changing magnetic field, so current won't flow. If that was the case, we would be able to produce free energy. But there is no free energy. We have to apply a force to push this magnet through this coil. And then what we end up doing is we end up producing the flow of electrons. And that flow of electrons can enable us to put a light bulb in here and light it up, or any electric appliance. What's this idea? This is the idea of an electric generator. This is how generators work. Now, they're not always organized or put together, assembled in this way. Usually what happens is we have magnets that are spinning next to a coil of wire, and there's a whole bunch of different configurations. But the basic fundamental concept is that if we take this magnet and move it into the coil, that's increasing or decreasing the magnetic field, and we will get current flow. We will have made electricity. Now, if we take a soft piece of iron, so this is a material in which its domains can easily align, and if we wrap it in current-carrying wire, it will make a magnet. So when it's just a soft piece of iron, it is a temporary magnet. It's not a magnet at first, but as we put current in it, the current flows and all of the domains align, and this becomes a magnet. As soon as we turn this off, it stops being a magnet. So this has a name. It's called an electromagnet, and it's just a way to have a magnet that turns on and off. There's also a rule that you don't need to know for Regents curriculum, but if you're taking a more advanced physics course, for this you take your left hand, you curl your fingers in the direction that the wires are going around the magnet, and your thumb becomes the north pole of the magnet, and this would become the south. The last thing that you should know about magnets is that if we have a permanent magnet and we snap it in half, what happens? Do we get a south pole separated from a north pole? Well, no. We end up getting two new smaller magnets. So this becomes south, this becomes north, and that becomes south. And the reason that this is the case is because it's not possible to trap a pole by itself. That's the idea of a monopole, and no one's been ever able to show a south pole without a north pole, or a north pole without a south pole. So they go together. A couple of other things that you should know, which is that there are things that disrupt the domains. So even if we have a permanent magnet, it doesn't mean it's always going to be permanent. Heat will unalign the domains, and also dropping the magnet, or if you took a hammer and hit the magnet over and over, these domains would start to get jumbled up, and it would no longer be a permanent magnet.